Hello everyone, how are you all doing tonight? I've had some really cool stuff happen today. Good morning, hello Gamma, great to see ya. I've got some cool stuff. One, I have a new Switch now. I am so happy. It's just really nice to have a new Switch again. Yay. Yeah, my old one has been kinda kicking it recently. So now that I have a new one, I might actually be able to, did someone overcharge your batteries? Yeah, no, the fan on my Switch is, broken and such. It's it rattles a lot all the time now, and it was really worrying me, so I'm glad I've got a new one that's better, and I might be able to actually, stream Switch games with it at some point if I can, get a capture card. But yeah, yeah, I am super happy about that. And also, I put out my new short story, and people have really liked it, and I am really happy. I'm just so happy that, people have, enjoyed it. For folks who have not seen it yet, if I can, boom. Yeah, I'm just really happy with this new short story. Yeah, Happy Robot? Yeah, people have been really happy with it. I'm really happy with it. It's the biggest, it's the biggest short story I've written yet, and I'm just so proud of it. I managed to make something, really happy and cozy, and I'm just so happy. Yeah, okay. Yeah, tonight I am gonna be learning more of the Rust programming language. I'm really excited for that. Tonight we're gonna be starting out with smart pointers, which is gonna be cool, gonna be fun, gonna be neat. Yeah, anyway. Oh!
I can't believe it's been a whole stinkin' year. It's been a great one, Lemma.
Hello, Non! Thank you very much for subscribing at Tier 1 for 12 months! Wow! Yeah, it's been great having you here. It's always nice to have you around, and I hope you're doing good. Yeah. Without further ado, how about we get on over? Right, I forgot to launch that. Up. SB code and SB web browser. That one. Up. Boom. Yeah, so, let's get going. A pointer is a general concept for a variable that contains an address in memory. This address refers to or points at some other data. The most common kind of pointer in Rust is a reference, which we learned about in Chapter 4. Oh no, pointers, yeah. Fun times. References are indicated by the AND symbol and borrow the value they point to. Surprised in C++, yeah. They don't have any special capabilities other than referring to data. Also, they don't have any overhead and are the kind of pointer we use most often. Smart pointers, on the other hand, are data structures that not only act like a pointer, but also have additional metadata and capabilities. The concept of smart pointers isn't unique to Rust. Smart pointers originated in C++ and exist in other languages as well. Yeah. In Rust, the different smart pointers defined in the standard library provide functionality beyond that provided by references. One example we'll explore in this chapter is the reference counting smart pointer type. This pointer enables you to have multiple owners of data by keeping track of the number of owners and, when no owners remain, cleaning up the data. Pointers, hello Maddie! Great to see ya! In Rust, which uses the concept of ownership and borrowing, an additional difference between references and smart pointers that references are pointers that only borrow data. In contrast, in many cases, smart pointers own the data they point to, which is cool. I've already encountered a few smart pointers in this book, such as a string and a vec. Alright, though we didn't call them smart pointers at the time. I think that's really good. Both these types count as smart pointers because they own some memory and allow you to manipulate it. They also have metadata, such as capacity and extra capabilities or guarantees, such as with string and string, its data will always be UTF-8. Smart pointers are usually implemented using structs. A characteristic that distinguishes a smart pointer from an ordinary struct is that smart pointers implement deref and drop. The deref trait allows an instance of the smart pointer struct to behave like a reference, so that you can write code that works with either references or smart pointers. The drop trait allows you to customize the code that is run when an instance of the smart pointer goes out of scope. In this chapter, we'll discuss both traits and demonstrate why they're important to smart pointers. Now, I remember seeing an article, this is getting a bit ahead of the book, but like, aren't mutexes like smart pointers in Rust? So that like, when they run drop, they will automatically unlock? Yeah. Given that the smart pointer pattern is a general design pattern used frequently, mutex locks are, yeah. Yep. Yeah, the locks, I mean, yeah. Given that the smart pointer pattern is a general design pattern used frequently in Rust, this chapter won't cover every existing smart pointer. Many libraries have their own smart pointers, and you can even write your own. We'll cover the most common smart pointers in the standard library. Box T for allocating values on the heap. RCT, a reference counting type that enables multiple ownership. RefT and RefMuteT access through RefCellT, a type that enforces the borrowing rules at runtime instead of compile time. Yeah, not entirely sure about mutexes themselves, so the majority of time you're using Arc with them, but yeah. Yeah. In addition, we'll cover the interior mutability pattern, where an immutable type exposes an API for mutating an interior value. We'll also discuss reference cycles, how they can leak memory and how to prevent them. Let's dive in. Alright. First up, most straightforward smart pointer is a box, whose type is written box T. Boxes allow you to store data on the heap rather than the stack. Recycling's the worst with smart pointers. Fun. Yeah. Alright. So, boxes don't have performance overhead other than storing their data on the heap instead of on the stack. But they don't have many extra capabilities either. You'll use them most often when you have a type whose size can't be known at compile time and you want to use a value of that type in a context that requires an exact size. Yeah. When you have a large amount of data and you want to transfer ownership but ensure the data won't be copied when you do so. Or when you want to own a value and you care only that it's a type that implements a particular trait rather than being of a specific type. Safe Rust stops you from mem leaks. Box Concon leak exists. Oh boy. Demonstrate the first situation in recurring or enabling recursive types with boxes later down, okay? In the second case, transferring ownership of a large amount of data can take a long time because data is copied around on the stack, so we can store the large amount of data in a box. Then only the small amount of pointer data is copied around on the stack while the data it references stays in one place on the heap. I was reading with the wrong intonation, yeah. Yeah. You typed the wrong, yeah. Right. Then, third case is known as a trait object, and chapter 17 devotes an entire section using trait objects that allow for values of different types just to that topic, okay. Yeah, box leak just leaks memory, amazing. Trait objects, yeah, oh boy. I mean, yeah. Alright, before we discuss the use case for Boxy, we'll cover the syntax and how to interact with values. Alright, so. Okay, so it looks like Box is in the preamble, so let Box. I need a new keyboard. I need a new keyboard for this computer. This, like, because the, like, some of the keys on my, like, laptop keyboard are broken, I've been using, like, a mechanical keyboard on top of it, and it's got MX Blues, and oh my god, they are so good. I need to get a new, like, mechanical keyboard with, like, tactile switches. The ones I've got on here are, they are chalk browns, which I believe are just like a linear switch. Yeah. Yeah, it's heavily suggest the code keyboard. Clicking memory is useful in some circumstances. I've used it in WASM because I need a closure to live forever. Yeah. Live forever, yeah. Basically, that just lets you make something exist permanently. Yeah. Got like 1 second of delay in my code somewhere and I don't know where. Oh no! Yeah, like, controlled memory leaking does seem like it could have uses. Also, I will definitely, will probably do well with, trade objects, just because I come from Java. Comes with MX clears, which are tactile and quiet. But I want loud! Then I was using memforget, which also leaks memory. Like, yeah, like, I love, like, just, I should make it very clear. I like having a loud, annoying keyboard. It makes me feel powerful and actually helps me focus. Get distracted when my own keyboard's screaming at me. Yeah, that's fair. The clacky clack is louder, it makes the code better. Yeah, trade objects are not like Java, they're much worse. Oh no. But yeah. Yeah, I will take a look at the code keyboard. Oh, that's money, huh? That's money, huh? Oh boy. Well, that's something for the throne. Got it. Much worse. That's not legit. Yeah, recently got new switches for my keyboard because it was too loud. Yeah, it's a bit spendy for sure, but yeah. Yeah, well, to be, yeah, like, either way, I think having, like, a bit of, like, dynamic dispatch is good, but I can get why there can be issues with it. Yeah. The keyboard is RGB, it makes the code faster, yeah. Oh wait, the code keyboard is just like white LEDs, Also, I also am very picky about my keycaps for some reason. I really like DSA profile keycaps. I'm not quite sure why, but I really like them. Yeah. What's that lemma? DSA profile? Adding RGB to anything makes it faster. This is scientifically proven. Let me just, like, quickly, like, grab, like, a reference image for, like, keycap profiles. Trait objects can't really downcast, so you can only access the methods on the trait, and there's a lot of limitations in what makes a trait object safe. Yeah. Price that's small, what the fuck? Alright, I'll just blow this up, it'll look like shit, but yeah. This is like just what a few different keycaps look like. I like the DSA ones because they're all uniform and they just feel and look nice. Some folks like prefer like different like profiles for each row and such. I don't. I just prefer like the DSA ones. Yeah. And my keyboard's DSA, I think, yeah. Basically, anywhere you can, you want to use generic over trait objects. Yeah, that's fair. Yeah, because you can do, like, the generic with where and such. Where's my... There. Alright. Find a variable b to have a value. Yeah. Oh yeah, I should also println ah, put the b equals 5. Okay. And that'll just work here as well. Yep, yay. I think it's really cool that they can just have like hey, run this code button on the like the documentation. Yeah. Find the variable b to have value of a box that points to the value 5, which is heap allocated. The program will print b equals 5. In this case, we can access the data in the box similar to how we would if this data were on the stack. Just like any owned value, when a box goes out of scope, as b does at the end of main, it will be deallocated. Deallocation happens as after the box and the data it points to. Neat! Putting a single value on the heap isn't very useful, so you don't use boxes by themselves in this way very often. Having values like a single I32 on the stack, where they're stored by default, is more appropriate in the majority of situations. Let's look at a case where boxes allow us to define types that we wouldn't be allowed to if we didn't have boxes. Recursive types. Oh, recursive types. Fuck yeah. Let's go vec int. Let's look at a case where boxes allow us to define types that we wouldn't be allowed to. Yep. At compile time, Rust needs to know how much space a type takes up. One type size can't be known at compile time as a recursive type, where a value can have, as part of itself, another value of the same type. Oh, that's like a linked list, not a compile time list. Yeah. Yeah. Because this nesting of values could theoretically continue infinitely, Rust doesn't know how much space a value of a recursive type needs. However, boxes have a known size, so by inserting a box in a recursive type def, you can have recursive types. Let's explore the cons list, which is a data type common in functional programming languages as an example of recursive type. The cons list type will define is straightforward except for the recursion. Now, learning Rust, just let metal oxidize, that shouldn't be that hard, right? Hello, monks! Welcome to the stream! Yeah, therefore, the concepts in the example we'll work with will be useful anytime you get into more complex situations involving recursive types. A cons list is a data structure that comes from Lisp. In Lisp, the cons function, short for construct function, constructs a new pair from its two arguments, which usually are a single value and another pair. These pairs containing pairs form a list. Okay. Alright, yeah, I can see that, yeah. Recursive types, yeah. Try to make a cons list with heterogeneous generic ones, but I used it wrong, oh no. Only time I've used them is for trees, oh boy. Alright. Cons function, yeah. Cons function is, made its way into more general functional programming jargon. To cons x onto y informally means to construct a new container instance by putting the element x at the start of this new container, followed by the container y. Alright? Yay! Explaining jargon. That's a good thing. Jargon sucks. Each item in a cons list contains two elements, the value of the current item and the next item. Last item in the list only contains a value called nil without a next item. A cons list is produced by recursively calling the cons function. Canonical name to denote the base case of the recursion is nil. Note that this is not the same as the null or nil concept in Chapter 6, which is an invalid or absent value. Alright. Although functional programming languages use con lists frequently, not commonly used data structure in Rust. Most of the time when you have to use a list of items, vect is a better choice to use. Yeah, yeah, don't use linked lists in Rust. You just really do not need to. You don't need to use a linked list. They're slow, they're not performant. Like, there's just so many better ways to do a list. Alright, so... most of the time when you have a list of items, vector is a better choice to use. Yep. Other more complex recursive data types are useful in various situations, but by starting with the cons list, we can explore our boxes let us define a recursive data type without much distraction. Okay, let's write some illegal code first. List cons I30 list nil. That's illegal. Recursive type list has infinite size. Yep. Is there like anything I can wanna check Rust Analyzer, because I don't like having like that. I don't like the helper things for like enum keywords or such. Where's extension setting? Oh, actually, linked lists are not as bad as most things lead you to believe. Depending on their use case, can be far more performant than a dynamic array. Yeah. This is not actually... I like hover, there. I'm gonna turn off dock hover. Yeah. There. Yeah, now it just tells me theirs. That's much better. I like dock hover can be nice, but I prefer it not. Now, those cases are generally less common than the cases where vec is better. Yeah. Yeah. Implementing cons list that holds only I32 values. We could have implemented using generics. Yeah, as to define a cons list that could store any type of value. Alright. Using list type to store list 1, 2, 3 would look like this, okay. Yeah. But first cons value holds 1 in another list. Yeah, so then we could like just have that. So like let list cons 1 cons 2 cons no. Boom. Alright. Save that and deal. There. Yeah, you can't find it in this. Why can't you find it? That legal? Oh, I think it's just cause like enum list isn't legal, so it doesn't work. So that won't work at all. Okay, yeah. Yep. So insert some indirections. So that'll be a box list. Dead. Why can't you find that? I'm confused as why. Yeah, you need list cons. Oh right, yeah. A list nil. Yeah, and then you'd have to like box, so yeah. Yeah, this, like, that resolves, that doesn't, yeah. Can you import from the list namespace? Yes. Right. You understand linked lists are better when you're operating on the front and back elements of the list. You need to do things in the middle regularly, better use vec, yeah. Thank you very much, Russ. No more absolute paths to statically import my own enum members, yeah. A bit more, yeah, hash maps, tree lists, graph trees, all much better using linked lists than trying to shove them into a vector, yeah. But, like, that's why they've got, like, types for those, too. Like, that's the big thing, is, like, in Rust, you almost never need to use a linked list because it provides all those data types for you. In C or such, like, that's a different story, but Rust is meant to have that for you. Yeah, like, you should never, like, directly use a linked list in Rust because anywhere where a linked list would work better is already written in the standard lib. Right, yep, so, yep, this is illegal. There shows the type has infinite size, that's because it's recursive. So. Yep, recall message, yep, so, about all this. Determine how much space a mess to allocate, Issue isn't about making the type, it's about thinking the problem space, yeah. Right, yeah, Alright, so, taking a look here to yeah, yay, under the hood stuff, hi! Hello, Dashfo507, welcome to the stream! I'm learning how to write Rust tonight, and it's pretty cool. Yeah, ooh, peek under the hood time, peek under the hood time. To determine how much space to allocate for a message value, Rust goes through each of the variants to see which variant needs the most space. Rust sees that message quit doesn't need any space, message move needs enough space to store I32 values, and so forth. Because only one variant will be used, the most space a message value will need is the space it would take to store the largest of its variants. Contrast this with what happens when Rust tries to determine how much space a recursive type like the list needs. The compiler starts by looking at the cons variant, which holds a value of type I32 and type of list. There you need, so you need the amount of space equal to an I32 plus a list, which is all the way down. Yeah, basically just goes to infinity. So, box time! We're gonna box list. And this suggestion, indirection, means that instead of storing a value directly, we'll change the data structure to store the value indirectly by storing a pointer to it instead. Also, linked list doesn't necessarily mean each link is allocated separately. Yeah. That is fair. Yeah, now that I can do that, then I can just box. And this is gonna take a lot more, but yeah. Now this is illegal because, now I need a box. Box. Nil. Good? Yay! This takes up a lot of space, yeah. Proof of none, yeah. I mean, linked list has nothing to do with an allocation scheme, yeah. So it's still linked list, yeah. Yeah, it's just that, like, a lot of the time, like, you can just instead, like, a lot of the time, like, the slight memory bloat of, like, a pre-allocated list can just be fine. You can eat it, but yeah. You can still jump by one and allocate in groups, yeah. Because a box is a pointer, Rust always knows how much space a box needs. Pointer size doesn't change based on the amount of data. And now we have this long thing. That is, like, how many is that? Like, that is 1, 2, 3, 4, 5, 6 close parentheses in a row. What are we writing, Lisp? Yeah. Totally swap element order and keep it slightly more continuous. Yeah. Most of the things I mentioned are all best done with large Alex that are broken up, divided into different links. Yeah. Right, but yeah. Cons variant will need the size of an i32 plus the space to store the box's pointer data. Nil variant stores no values, so it needs less space than cons. Know that any list value will take up the size of an i32 plus the size of a box's pointer data. By using a box, we've broken the infinite recursive chain, so the compiler can figure out the size it needs to store a list value. Yay! Yep, shows what the cons variant looks like now. Yay, just box and U size. Yeah, box of U size. Boxes provide only the indirection and heap allocation. They don't have any other special capabilities like those we'll see with the other smart pointer types. They also don't have any performance overhead that these special capabilities incur, so they can be useful in cases like the cons list where the indirection is the only feature we need. We'll look at more use cases for boxes in Chapter 17 too. My experience when I'm doing large Alex, it's mostly just one big structure data that needs to be contiguous, like reading evacuate from disk, yeah. It's all, like, all programming is incredibly situational. There's, like, issues with, like, it's harder to, like, shuffle or sort or such a linked list, but yeah. Box is a smart pointer because it implements deref, which allows box to be treated like references. When a box goes out of scope, heap data the box is pointing to is cleaned up because it dropped. Let's explore these two traits more in detail, okay? They'll be even more important to the functionality provided by other smart pointer types. Okay, let's make some stuff. So deref allows you to customize the behavior of the reference operator. Yeah. In my personal game engine, I allocate a single 4 gig block at program start and just use that for the whole life of the program. Yeah. Why? Crashed it. There's something very wrong with my laptop, and I hope I can get a new one soon, because this is just annoying. Keeps having just these weird issues with apps crashing for, like, no reason. Yeah. No dynamic allocations whatsoever. Yeah. If you're not doing, like, dynamic allocations, then it isn't as big of a deal. Yeah. JVM uses Arena to sort C++ idalics. But yeah. Alright. Let's first look how the dereference operator works with regular references. Yeah. Then we'll try to define a custom type that behaves like box and see why the deref operator doesn't work like a reference on our newly defined type. We'll explore implementing deref makes it possible for smart pointers to work in ways similar to references. Then we'll look at Rust's deref coercion feature and how it lets us work with either references or smart pointers. I think, yeah, like, there's some coercions that are really good, like, deref coercion is neat. Alright, so, one big difference between my box and the real box, our version will not store its data on the heap. Let me just figure out this stuff. Yep. We're focusing just on deref, so where the data's actually stored less than more. Yeah. I had problems with deref coercion, maybe I was using it wrong, yeah. Yeah, like, coercion is, like, not always gonna work, but, like, at least having some coercion is nice. Yeah, like, coercion can have issues. Cough, cough. JavaScript. By the way, I've not gotten... Yeah, there haven't been any comments on, like, the issue I put into, like, Rust RFCs and such, so... Oh well. Regular reference is a type of pointer, and one way to think of a pointer is as an arrow to a value stored somewhere else. In listing 15.6, we create a reference to an i32 value, and then use the deref operator to follow the reference to the data. Alright, so... Like, for example, let x equals 5... let y equals, and assert ec 5x. Oh, I forgot to print 5x. Assert ec 5 reference y. Y dereference y. And then save, go. That problem, yeah, alright, yeah, no, I read that, okay, yeah. Alright, and all good. Variable x holds an I32 value 5. We set y to equal to reference to x. We can assert that x is equal to 5. However, if we want to make an assertion about the value in y, we have to use deref y to follow the reference to the value it's pointing to. Once we deref y, we have access to the integer value y is pointing to, so that we can compare with 5. If we didn't do that, then we'd just like be trying to compare an integer with with an address to an integer. Comparing a number and a reference to a number isn't allowed because they're different types. You must use the deref operator to follow the reference to the value it's pointing to. Pointer stuff! So, what if instead of using that, we'll make a box new x and run, and yep, assertion passed. Only difference between 15.7 and 15.6 is that here we set y to be an instance of a box pointing to a copied value of x rather than a reference pointing to the value of x. In the last assertion, we can use the deref operator to follow the box's pointer in the same way that we did when y was a reference. Next, we'll explore what is special about box_t that enables us to use the deref operator by defining our own box type. Alright, so struct my box T. Yeah, I like how if you have like only one thing in a struct like this, you can just like use like parentheses, but yeah. Right then, impl T my box T new x my box x. Alright. Find a struct named myBox and declare generic parameter t. Could you? I want to check. Is this? No, it does demand a block. It does demand a block for functions. You can't just have it in line. Okay. Or at least if you've got like the return type there, yeah. Find a struct named myBox and declare generic parameter t because we want our type to hold values of any type. MyBox type is a tuple struct with one element of type t. MyBox new takes one parameter of type t and returns MyBox and holds the value passed in. Alright, so then we can let x equals 5, let y equals MyBox 5, assert ec 5x assert x ec 5 deref y, and this is illegal because we don't deref. Yeah, we don't have deref. Struct TU8 is typically called a new type and it's just a name tuple. Yeah. Yeah, I like. Yeah, like. Name tuples are good. I like name tuples. They're convenient. Yeah, so this is illegal. Can't dereference that. Alright, so treating a type like a reference by implementing deref. So this is impl deref. No, not p. Getting my hands aligned on the keyboard is weird sometimes. Okay. Type target. No. Semicolon. Why is my right hand just not hitting the right key? Then deref and self and self target and self. Oh. Right, I have to use standard ref. Yeah. Python name tuples let you choose an element by index or name, yeah. And now if I run this, it should be legal. All good, yay. Alright, yay, we've got a deref. Fill in the body of deref with and self.o, so deref returns a reference to the value we want to access with star, okay? Main function in 59 that calls star on mybox.t value now compiles, and the assertions pass. Without deref, compiler can only dereference and references. Deref method gives the compiler the ability to take a value of any type that implements deref and call the deref method to get an and reference that it knows how to deref. Right? We can also, yep. Yeah, so behind the scenes, Rust actually ran star y.deref, yep. Or substitutes the star operator with a call to deref and then a plain dereference, so we don't have to think about whether or not we need to call the deref method, yay. This Rust feature lets us write code that functions identically whether we have a regular ref or a type that implements deref. And of course, like, just depending on, like, inlining and such, it might just, like, replace that all with, like, the and self.o and everything, but yeah. The reason deref returns a reference to a value and that the plain deref outside paren is still necessary is ownership, yay! If deref returned the value directly instead of a reference to the value, value would be moved out of self, which don't want, so we still need to do like a proper deref. Yep. No, star operator is replaced with a call to deref and then a call to the star operator just once each time we use the star in our code. Because the substitution of the star operator does not recurse infinitely, we end up with the data of type I32, which matches the 5 and assert. Yay. Deref coercion is a convenience that Rust performs on arguments to functions and methods. Deref coercion only works only on types that implement deref. Converts such a type into a reference to another type. So deref coercion can convert and string to and stir, okay? Yep. Does string implements deref so that it returns and stir, yep. Happens automatically when we pass a reference to a particular type's value as an argument to a function or method that doesn't match the parameter type in the function or method def, okay. Sequence of calls to the deref method converts the type we provided into the type the param needs. Deref coercion was added in Rust so that programmers writing function and method calls don't need to add as many explicit references, dereferences, and star. Deref coercion also lets us write more code that can work for either references or smart pointers. Let's see. To see deref coercion in action, let's use the mybox.t type we defined in listing 15.8 as well as the implementation of deref we added in listing 15.10. Okay, so hello name and println hello name. Right, so I see if freelist is an implementation of object recycling for linked lists. Okay. Right, so then let m equal box new Rust hello boom. keep hitting, because like there's different like layouts on this keyboard I'm using and like the one I've been using for my like desktop, I keep hitting what is on this keyboard, the FN key, whenever I want to hit control. Whoops. Yeah, now, this should be good. Yep, does hello Rust, yay. Because we're calling, yeah, here we're calling hello function with the argument and which is a reference to a mybox string. Because we implemented deref on mybox and listing 1510, Rust can turn and mybox string into and string by calling deref. Then you can deref and string to and stir. Yep, yay. If Rust didn't implement deref coercion, we'd have to write the code in listing 1513. Yep, fun, yeah. So yay, deref coercion. Starm dereferences mybox string into a string, then the and dot takes string slice of the string equal to the whole string to match signature below. Code without deref coercions is harder to read, write, and understand with all these symbols. Deref coercion allows Rust to handle these conversions for us automatically. Yay! When deref is defined for the types involved, Rust will analyze the types and use deref as many times as necessary to get a reference to match the parameter's types. The number of times that deref needs to be inserted is resolved at compile time, so there's no runtime dependency. Yay! Okay. Yay, then interaction with mutability. So so you can use deref mute to override star operator on mutable refs. Like, Rust does deref coercion when it finds type and trait implementations in 3 cases. So and t to and u when t is deref target equals u. Nmute t to nmute u when t is deref mute target equals u. Then nmute t to end u when t is deref target equals u. Okay. First 2 cases are the same except for mutability. First case states that if you have an and t implements deref to some type u, you can get u and u transparently. Yep, then for mutability. And trickier. Coerce a mutable reference to an immutable one. Reverse is not possible. You cannot make an immutable reference into a mutable one. Because of borrowing rules. Alright. Okay. Converting an immute ref to a mute ref will require initial immute ref is the only immute ref to data, but borrowing rules don't guarantee that. Okay. Boom. Then drop trait. Okay. Second trait important to the smart pointer pattern is drop, which lets you customize what happens when a value is about to go out of scope. You can provide an impl for drop on any type, and the code you specify can be used to release resources like files or network connections. Yay! Introducing drop in the context of smart pointers, because functionality drop is almost always used when implementing smart pointers. So, when box T is dropped, it will dealloc. Yep. Programmer must call code to free memory or resources every time they finish using an instance of a smart pointer. If they forget, system might become overloaded and crash. Oh no! In Rust, you can specify that a particular bit of code will be run whenever a value goes out of scope. The compiler will insert this automatically. Yay! As a result, you don't need to be careful about placing cleanup code everywhere in a program that an instance of a particular type is finished with. It still won't leak resources. Unless you use box.leak, which turns off it doing the drop. If you wanna. Specify the code to run, yep, you impl drop, so. Alright, so yeah, basically what we can do is if we put this up, so construct custom smart string, and we'll drop for custom Sorry for not answering there, okay, yeah. It's all good, then drop. Mute. Self. LN. Dropping. Custom. Art. Bang. Self. Data. And, here we can let's custom art data stuff. Don't. Why are you later? There and well, I forgot. Drop took an and mute self instead of just self. Yep. Well, you might want to like mutate stuff when dropping, but yeah. Most other languages call it pooling or something like that. Am I still live? I am. Yeah, very used to just calling it free list. Yeah. Just checking. Yeah, I'm live. Yeah. Stream dropped for a second for me. Yeah. I noticed that. Yeah, I noticed there might have been something like that. I'm glad it is back. It happened at the same time that Alienware was shouting at me, so I think their fault. But yeah, glad it is still going on. Stream broke for a sec. You're alive now. Yay! All right. Glad I'm still here. It looks like it did not interrupt like my recording or anything, so I'm all good. All right. I do wish I could get a better GPU at some time. It keeps like both like streaming and recording sometimes like overloads my GPU, but yeah, or GPU encoder, but yeah. Safe to blame on Alienware, yeah. And not that. And let C equals custom smart pointer data string from other stuff. Not there, boom. Println custom smart dated run. Unused doesn't matter because all we're checking is like that they're dropping. Yay! Woo! Yep, included in Prelude, so don't need to bring it into scope. Same with like, yeah. Drop being in Prelude is neat. This, can I? Right. Yeah, I'm gonna use that a bit longer, but yeah. Included in Prelude, provide an implementation for drop, method called, yeah. The impl drop, provide an impl for drop that calls println, yep. Yeah, where do you place any logic you wanted to run, yeah. So, like, that's with, like, mutex locks, they'll, like, unlock on drop and such, which is neat. I think that's cool. Printing some text here to demonstrate, yep. Create 2 instances CSP, yep, then print CSP is created. There's a CSP will go to scope and Russ will call the code we put into drop, printing our final message. Didn't need to call the drop explicitly. I could call drop explicitly instead of shadow deleting, yep. Russ auto called drop for us when an instance went out of scope, yep. Dropped in the reverse order creation, so D was dropped before C. Example gives you a visual guide to how drop method works. Usually you'd specify cleanup code, type needs to run, yep. Yeah, it, like, so, what's interesting about it, like, what's interesting about it dropping in, reverse order of creation is that means that the lifetime of C fully eclipses the lifetime of D. They aren't interweaving. Some people also like making a block instead of manual calling drop, but I don't like adding the intent, yep. Yeah, adding the intent, yeah, that's fair. Yeah, then you can also just use drop. Yeah, so not straightforward to disable the automatic drop. Disabling drop isn't usually necessary. The whole point of the drop trade is taken care of automatically. You might want to clean up a value early. when using smart pointers, yep, to manage locks, you might want to force drop increases so other code can acquire the lock. It doesn't let you call the drop traits drop method manually. Instead, you have to call standard mem drop. So, like, this is illegal. You cannot see drop. That is a crime. That's illegal. Let's use a destructor. Don't do that. Not okay. So, yep. So you standard drop C. Actually, oh yeah, no, you don't need that. You can just call drop C. Yeah. Then, if I recall, yeah, like adding the block sometimes doesn't work. Guess you could do letters equals C. Yeah. Now, here's a cool thing about this. Yep. We can just call drop, which is in prelude, yep. Call it functions in prelude so we can modify main, yeah. Now, here is the cool thing about this. You see this? This, yeah, drop is not magic. This function is not magic. It is just an empty block. It is just an empty block because it moves and then at the end of it, it'll automatically drop and the function returns. That's cool. I think that's just very, very cool. I like when code, like, this, like, just, it just doesn't have, and, yeah, like, a lot of the time, like, in source, like, in Rust source, you'll see, like, just something commented out for, like, impl detail, but yeah, like, fun drop is just an empty block. I think that, yeah, drop is so funny to look at, yeah, no, I think that is cool, yeah, that's awesome, yeah. I love things like that. I like it a lot. I think that's cool as hell. Much shorter than destruct or whatever, yeah. Like, I just think that's very silly and cool. Yeah. You can use code specified in drop in many ways to make cleanup convenient and safe, yep. Also don't have to worry about problems from accidentally cleaning up values still in use because own or ship. Now that we've examined box and some of the characteristics of smart pointers, let's take a look at a few others. So let's clean up. Sometimes Rust code is really funny to look at, yeah. That reminds me of another thing. GitHub Rust Rust. That reminds me of like another fun thing in Rust code, if I can find it. Library, then standard, I believe, yep, source. If I recall, it is in time. Ooh, let me pull that one up too. I'll check that one in a second. Yeah, over in like the time stuff, like this is where you've got like your like standard like time temporal quantification stuff. So you've got like your durations, you've got your instance, all that. Yep, yeah, all of that. System time, yeah, your system time. And what about getting instant : now? If that's let us know equals time instant now. And here we come upon a sad state of affairs. The whole point of instant is that it's monotonically increasing. But we found in the wild that it's not actually monotonically increasing for one reason or another. These appear to be OS and hardware level bugs, and there's not really a whole lot we can do about them. They've got a lot of issues. They've got, things just happens a lot in the wild. So they've just, like, there's an implementation, like, or there's like a platform specific impl for time instant actually monotonic. And if not, then they have to just like force it to be monotonic. Yeah. Which is very fun, yeah. hopefully mitigate the impact of this, a few platforms excluded as these at least haven't gone backwards yet. Yeah, like OpenBSD, Linux on ARM64, basically all options for Windows x86. There's some Linux ARM64. Fun stuff. Yeah. Programmers believe a lot of falsehoods about time. Yeah. Okay, what's this one? Hub unsafe function. Change lifetime const. Okay, yeah. And yeah. Borrow a deref x as deref con. Partially to ensure the reference does not become invalid, object has to outlive the reference. Fun. This is in dash map, which is just a fast map, yeah. Just changes lifetime of any reference, yeah. Yeah. The as star quantity is casting to an immutable pointer, yeah. That it derefs and then references and breaks all of the lifetime rules if used randomly. Yep. That's why it's unsafe. Yeah. Reference counted smart pointer. In the majority of cases, ownership is clear. You know exactly which variable owns a given value. However, there are cases when a single value might have multiple owners. In graph data structures, multiple edges might point to the same node, and that node is conceptually owned by all the edges that point to it. A node shouldn't be cleaned up unless it doesn't have any edges pointing to it. So there is multi-ownership in Rust, okay. That is using the reference counting type, okay? Keeps track of the number of references to determine whether or not the value is still in use. If there's 0 references to a value, the value can be cleaned up. That just counts and drop, okay, yeah. Yep. When one person enters to watch, they turn it on. Others can come in and watch. When the last person leaves the room, they turn it off. No longer being used. Why am I getting a lot of I'm getting a lot of noise in my headphones now for some reason. Oh, there it goes. All good. And it wasn't showing up on. Yeah. Yeah. I mean, yeah. It seems like it was just from my headset, so it's fine. Get a little static while mine is charging, yeah. I've got wired headphones, but yeah. Yep. Reference counter when we want to allocate some data on the heap from multiple parts of our program to read, and we can't determine at compile time which part we'll use at last. Okay. If we knew which part would finish last, we could just make that part the data's owner, and the normal ownership rules enforced at compile time would take effect. Reference counter key is only for use in single-threaded scenarios. Yeah, don't use reference counting for multi-thread, because then you can't really, then you can't track as well. But yeah. Yeah. When we discuss concurrency in chapter 16, the next one, we'll cover how to do ref counting in multi-threaded programs. Ooh, what's this, man? Ooh, think in standard lib. Okay. Another funny Russian. Alright, so, yeah. Yep, makes clone for the arc pointer, yep. Yeah, however, we need to guard against massive ref counts in case someone is memed for getting arcs. If we don't do this, the count can overflow and users will use after free. Racially saturate to eye-size max on the assumption that there aren't about 2 billion threads incrementing the reference count at once. Yep. Branch will never be taken in any realistic program, yep. Yep. Okay, yeah. I don't like... that's not a good use there, but yeah. But yeah. Yeah, basically, if there are too many references, something is wrong. Yeah. Let's return to our cons list example. Okay, yep. Recall that we defined it using box. This time, just bored if someone forgets the arc enough, yeah. Alright, so. Yep, recall we defined it using box. This time we'll create two lists that both share ownership of a third list. This looks like 15.3. Hey, that looks a bit like a tree. Or something. I know they could just forget the entirely, yeah. Yeah. We'll create list A that contains 5 and then 10. Then we'll make two more lists, B that starts with 3 and C that starts with 4. Both B and C lists will then continue on to the first A list containing 5 and 10. In other words, both lists will share the first list containing 5 and 10. So, yeah, if we, like, just bring our stuff back for now, so, list, cons, I32, box, list, nil, rate, list, on, nil. Then, if we let A equals cons, 5, box, 10, box, new, nil. Then we let B equal cons, 3, box, A, and let C equals cons, 4, box, A. That's illegal because box new takes ownership and that moves. Yeah, don't want to support it. Sounds good. Yeah. All right. Yeah, ownership issues. So, yep, they own the data they hold. So when we create B, A is moved to B and B now owns A. Then when we try to use A again, yeah, we can't because A's been moved. Oh boy. Could change the def to hold references instead, but then we'd have to specify lifetimes. Could be specifying every element in the list will live. Oh! Baby Beans, thank you very much for subscribing at Tier 1 for 9 months. Thank you for continuing to use LMOS. Specifying lifetime parameters would be specifying every element in the list will live at least along the entire list. Bar checker wouldn't let us compile let A, const 10, and nil, because temporary nil would be dropped before A could take whoops. Well, I opened my Rust Eclipse instance, and I had the const matrix program I was thinking of open. Alright, so, instead, we're gonna change this to a ref count. And that means we gotta use standard ref count RC. Just change all to RC. Not. Oh, RC clone, okay. Borrow. Okay, got it. So it says clone. Oh, gotta RC new this all. Boom. So yeah, you can clone an RC just to like bring it everywhere. Need to add a use statement to bring RCT into scope because it's non-prelude. Yep. Right, yep. Stored in a new RC list. Then we create B and C. We use RC clone function and pass a reference to the RC list in A as an argument. We could have called A clone rather than RC clone and A, but Rust convention is to use RC clone in this case. Implementation of RC clone doesn't make a deep copy, yet like most types implementations of clones do, so that only increments the reference count. So, like, so basically just doing this means that you don't, because reference counting is handling this, it'll just be faster. Right, yeah, Right, yeah. Impl of RC clone doesn't deep copy, so we can just do that for it to be faster. Yep. So cloning just bumps the ref count. So we can like throw a few like prints in, so println count after RC strong count A, and this down here. If we do, then if we put C in a block, which does have like don't want if it's been saying like I tried to like figure out what's going on with like things crashing with like the like system-wide console, but I'm just not getting anything. There's no like, hey, this app crashed or whatever. Is annoying, and I hope I can figure out why the fuck my computer isn't working. Why my laptop is just randomly crashing things all the time, yeah. Ooh, someone else's header, I'll just list impl. Ooh. Yeah, represents the most basic non-MTH list. Volume head, yeah, is held in head while it's tells another H list. Yep, nice. Yeah, stuff like that. Got it. I just had an idea. Hey, y'all can keep a secret, right? Y'all can keep a secret. I can trust y'all. Because I think there's something I've been just getting, yeah, like, there's something I've really been waiting to try out but haven't gotten a chance to yet. So, y'all can keep a secret, yeah? I'm gonna keep working on this, just... I'm just gonna quickly after dropping once I'm done with like this one, run. Yep, 1 2 3. Yay. Yeah, that works automatically. Woohoo! Hooray for standard lib. So y'all can keep a secret. Give me just a minute, okay? Ba 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 da ba 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 da ba ba ba. Hey. Ready. Ready. Right. And one more thing. I don't think they'll appear on stream. Yeah, with like where I've got everything placed. Let me just... Yeah. That'll work just fine. Hey! Y'all ready? Because you're gonna see this. 3, 2, 1. Do it. I want it. Alright, because I'm not on an. I just. Yeah. Nothing changed. I thought I could, like, use the stinger transition to change between 2 different versions of a scene. I can't, How? Actually. Fuck it. Hi! Oh, it's so good. It's so good. Hi, Sella! God, y'all. The Wiggles, yeah, Still, I've got a bit of an outline, but oh well, I can figure out that later, yeah. I've just been, yeah. Not like a formal reveal or anything, just messing around with it for a night. Oh, it's so good. I opened VTuber and I'm like, oh, shouldn't need to get Dilemma, yeah. Yeah, this isn't like a formal reveal, there's still just a bit that is missing, but there's a lot that's already here. You can tell. Yeah, I am gonna quickly... Up. There. God, it looks so good, yeah. I do need to fix the outline on it. I can just get that sorted, but yeah. Hey y'all, wanna see something cute as shit? Wanna see something cute as shit? Other than like these amazing wiggles. Check out these wiggles, y'all. It's so good, y'all. Y'all. Just y'all. Yeah, like, Kira and Kieran have done the best work. The best work with this model. It's so fucking good. It just... Everything about it is just amazing. So good. It's so good. I am so happy with this model. It's so good. But yeah, I'm just gonna stick with this for the rest of the night, I think. I still, like, need to adjust the, like, facial expressions just a bit. Like, it's not tracking perfectly, but it's doing, like, decently well. I might, like, see if I can, like, yeah, like, figure out if Kieran can, like, help the mouth, like, move in a few other ways, but yeah, Anyway, let's keep going now. Gosh, yeah, no. Huge props to Kira for the art, Kieran for the rigging. I've got expressions, like, I can, like, go all pink and it's cute as hell. I've got, like, ideas for, like, other things I could do with it, but, or at least with, like, the pink and such. I've got, like, these cute little hearts, these adorable little hearts. I've got a code face. Right, that was, oh no, I never did actually get that expression over onto, like, my model here. Oh well, I can do that. VTube Studio won't throw too much of a tantrum if I edit the model while I'm using it, right? That should be fine. It should be fine, hopefully. So, yeah, actually, wait, no, I'm just gonna close VTube Studio real quick and then pull it back up. Just because I remember there is some stuff in, like, the model JSON that needed to be adjusted. You're lucky if it either hot reloads or uses the unchanged version. Yeah. Yeah, alright, just need to do that, yeah, just need, so, model JSON, that one, that, and that'll be in data. Apps. All the way at the bottom. Go, data. Streaming assets? Yeah, live 2D models, lemma. Boom. Oh. And if I boot it back up, Ah, oh, that's right, I need to say something. Oh, lemma, you're fucking adorable. Oh, Ah, right. Booting up, that's... Ah, thank you. Yeah, now, if I, just quickly adjust my expression. Thank you for the hydrate. Half. There. Now, close that. Ah, there, that's better. Oh, thank you for the hydrate and posture check. Yeah, now I've got like a what the fuck like expression. I think it's really cute, but yeah, y'all, this model's just amazing. It's just amazing. I'm so happy with it. Yeah, I'm gonna use this for the rest of the night, I think. Just like, not like a big event, just like, as like, hey, I'm really happy with this. Why is my play stuff getting... Which did something... Oh, there. I did something and I hit a weird button somehow? Yeah. Stream dropped for a second for me, yeah. Oh well. Wait, no, that's old chat. Why is it such old chat? Stream is having a fucking moment. Apology, or Twitches, but yeah. Apologies, but yeah, anyway. Yeah. How about we keep going? Yeah, now we can, like, do this. It's got, like, reference counting. Yay. Alright, yay. So, we can't see in this one. B and A go to scope the end count is then 0, and the RC list is cleaned up completely. Yay. Posture check. Yeah. Via mutable references, RC allows you to share data between multiple parts of your program for reading only. If RCP allowed you to have multiple mutable references, it might violate a borrowing rule. Yep. And multiple mutable borrows to the same place can cause data races. But being able to mutate data is very useful. In the next section, we'll discuss the interior mutability pattern and the ref cell T type that you can use in conjunction with an RCT to work with this immutability restriction. Alright? Ref cell and the interior mutability pattern. Interior mutability is a design pattern, allows you to mutate data even when there are mutable refs. Action is disallowed by borrowing rules. To mutate pattern uses unsafe code inside a data structure to bend Rust's unusual rules, or usual rules that govern mutation and borrowing. We haven't yet covered unsafe code. We will in chapter 19, all the way at the end. We can use types that use the interior mutability pattern when we can ensure the borrowing rules will be followed at runtime, even though the compiler can't guarantee that. The unsafe code involved is then wrapped in a safe API, and the outer type is still immutable. Let's look at ref cells. Okay. So, ref cell represents single ownership over the data it holds. Any given time you can have either one mutable ref or any other number of mutable refs. References must always be valid, okay. Borrowing rules and invariants are enforced at compile time. With ref cell, invariants are enforced at runtime. With refs, if you break these rules, you'll get a compiler error. With ref cell, your program will panic! Hey. Advantages of checking borrowing rules at compile time are that errors will be caught sooner in the dev process. And there's no impact on runtime performance because all analysis is completed beforehand. For those reasons, checking borrowing rules at compile time is the best choice. That's why That's Rust default. Yep. Barring rules runtime that certain memory-safe action scenarios are allowed when they're disallowed by compile time checks. Static analysis is inherently conservative. Some code properties are impossible to detect by analyzing. Yeah, look how cute it is. Oh, keep looking over and seeing them all in one. Sella. Thank you so much. God. Stella, that makes me really happy. Thank you so much. Yeah. It's so good. I'm just so happy with it. Things have been going really well for me, and I'm really happy. Yep. Because some analysis is impossible if the Rust compiler can't be sure the compiles with ownership rules. Yep. Most famous example is halt. Yeah, so like you can't solve the halting problem with static analysis. You just can't. Not that we know, at least. Yeah. Yep. Beyond the scope of this book, but it's interesting to research. Yeah. If Rust accepted an incorrect program, users wouldn't be able to trust the guarantees. However, if Rust rejects a correct program, programmer will be inconvenienced, but nothing catastrophic can occur, yeah. You can do subsets and guesses, but yeah. RefCell is useful when you're not sure your code follows the borrowing rules, but the compiler is unable to understand and guarantee that. Similar to RC, RefCell is only for use in single-threaded scenarios and will give you a compile time error if you try using it in multi-threads, yeah. My mind is expanding. Hello, Mr. Mango. Yeah. Hello, Mango. It's great to see ya. Yeah. Alright, so. Alright. So, RC enables multiple owners. Box allows mutable or immutable borrows. Compile time. RC, yep, so RC is multiple owners. Boxes, immutable or mutable borrows at compile time. And RefCell is, RefCell allows mutable borrows at runtime. Yeah, RC allows only immutable borrows at compile time, yeah. Yeah, RefCell allows mutable borrows. You can mutate the value inside of RefCell even when the RefCell itself is immutable. Right? Yeah. Mutating inside an immutable value is interior mutability pattern. Okay. Let's take a look. So, let x equals 5. Let y equals and mute x. That's illegal! Because you can't mutable borrow something immutable. There is situations in which it could be useful for a value to mutate itself, but appear mutable to other code. Yay, yeah, interior mutability is good. Code outside the values methods would not be able to mutate. Using RefCell is one way to get the ability to have interior mute, but doesn't get around the borrowing rules completely. Borrow checker allows this interior mutability, and borrowing rules are checked at runtime instead. You'll still, yeah, that means you'll get a panic instead of a compiler error. So, mock objects. A test double is the general programming concept for a type used in place of another type during testing. Mock tests are specific types of test doubles that record what happens during a test so you can assert that the correct actions took place. Rust doesn't have objects in the same sense as other languages have objects, and Rust doesn't have mock object functionality built in. However, you can definitely create a struct that will serve the same purposes as a mock object. Here's the we'll create a library that tracks a value against a maximum and sends messages based on how close to the max current is. This library could be used to keep track of user quota for API calls, for example, but yeah. Alright, so we'll just get rid of this code because it's illegal. we have a lot of stuff here. I might take out the cacher stuff at some point, but it's not like being used, so it'll just be cut up. Yeah. Hub trait messenger unsend and self message and stir hub struct limit tracker prime a messenger and prime a key value use size max use size. Right. Then simple prime a t limit tracker a t where messenger illegal? Oh, no, comma. That. Oh no, that's not how you. Right. Hub fun messenger and max size limit tracker limit tracker. Right. Oops. Messenger value O and right. Hub fun set value and mute self value size self value equals value. Oh no, then there's a lot more in that. Okay, let percentage of max self value as f6 or self max or if percentage of max greater than equal 1 O self messenger send error or quota else if max greater than equal 9 self messenger and urgent you've used up 90% quota else if percentage max greater than equal 0.75 self messenger send warning you've up over 75% of your quota. All right. Yay, all good. Yep, one important part, Messenger has one method called send that takes an immutable reference to self in the text of the message. This trait is the interface our mock object needs to implement so that the mock can be used in the same way a real object is. Okay. Other important part is that want to test the behavior of the setValue method on limit tracker. We can change what we pass in for the value parameter, but setValue doesn't return anything for us to make assertions on. We want to be able to say that if we create a limit tracker with something that implements the messenger trait in a particular value for max, when we pass different numbers for value, the messenger is told to send the appropriate message. Okay. We need a mock that, instead of sending an email or text message when we call send, will only keep track of the messages it's told to send. We can create a new instance of the mock, create a limit tracker that uses the mock, and call the set value method on limit tracker, and then check the mock has the messages we expect. Listing 1521 shows an attempt to implement a mock to do that, but the bar checker won't allow it. So config test mod tests star mock and messages spec string and impl mock new mock messenger sent messages spec empty. All right, then impl messenger for mock messenger and send and self messenger self sent messages that push string from message there and test, and it sends an over 75 forming not message. Let mock messenger new. Let mute limit tracker equals limit tracker and mock messenger 100 limit tracker set value 80 assert ec mock messengers sent messages len len 1 then problems. Not bar is mutable as it's behind an and reference. Yep, so that is illegal. Alright. Hello, Sunroses! Wonderful to see you! Oh yeah. It defines mock messenger that has sent messages filled with vec a string to keep track of messages. Yeah. Also define an associated function new to make it convenient to create new mock messenger values that start with an empty list of messages. Then implement messenger, yep. Then take message passed in as parameter and store it. Yep. In the test we're just making sure that all works. New limit tracker, yep. Set value to 80, which is more than 75. Insert list of messages that mock messengers keep track of should now have one message in it. But you've got some issues here. Yeah, this is an immutable ref. Yeah, was just stopping by to say hello, hope you're having fun. I am, yeah. I'm just messing around with my new model. Ah, it's so good. It's so good. I'm just so happy with it. Yeah. It does not have tongue tracking yet. It will, so I can, like, stick out my tongue when I yawn and such. Yeah. Yeah. Send message takes an immutable ref to self. Yep. We also can't take the suggestion from the error text and muse itself because then it wouldn't match messenger. So we've gotta get a ref cell or such. So what we're gonna do instead is standard cell ref cell. So ref cell text string. We're gonna do a ref cell up. Then gonna add self-set messages, borrow mute, and then push. Yeah, beeps and boops. Yeah, kind of disorienting how when you move forwards away from the camera, it looks like the whole model scales. Yeah, that is like I can actually like turn that off, I believe. Yeah, I'm not sure how much I like it, especially because like it happens whenever I like move my head forward or back. I believe that is just movement config there. Now, like, I'm just gonna stick in place. Yay. Like, find myself a bit, but yeah. Wiggle, 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 wiggle. Oh, it's so good. I'm so happy. Jiggle physics, yeah. Yeah, I still do need to, like, configure my, like, tracking a bit more, but, it's just, I love the jiggle physics. They're just so good. Kieran did an amazing job. Yeah. Yeah, now we can just, borrow Outland. Yeah. Yay! Now this has a borrow mute, which then goes out of scope here, yeah. Okay, I can hear again. Oh. Yeah. Oh yeah, also while you're here, Sun Roses, an important thing. Right, yay, now this should work. Plop, yeah. Yay, test passed, woo. G the text, yeah, it's so good. It's so good. So good. I've got like blushy one, and like hearts and such. And I've got like a an oh no, what have I done or such. But yeah, it's so good. I really need to get like just a macro pad or such to be able to manage those. Yeah. Yeah, they're really good. Yeah. Another thing we've set is that whenever I puff my cheeks out, it'll like do like a bit of blush, so like it's so cute. So cute and good. I will have like a special reveal for it later or something maybe, yeah. Like, it's not entirely done. I've got like a few more ideas I want for it, like gotta have like a tongue sticking out. I've gotta like do some more like config, because like whenever I open my mouth like wide, like the eyes shrink, so like yeah, kind of like that, which I think I would prefer that to be like connected to like eyebrow raising instead, but yeah, we can figure it out. Woo! But yeah. Still an immutable borrow, yep. Call borrow mute to get a mutable ref. Then call push on the mutable ref to the vec to keep track of the messages sent during the test. Last change we'll have to make is in the assertion, yep, just like borrow there, yeah. It's love you, yeah, see ya! Been great having you here. Yeah. Okay. So, let's figure out how it works, because that's the best part about like the Rust talk, is it talks about that, yeah. When creating immutable and mutable references, we use and mute syntax respectively. With RefCell, we use borrow and borrow mute methods, which are part of the safe API that belongs to RefCell. Borrow method returns the smart pointer type reft, and borrow mute returns refmute. Both types implement deref, so we can treat them like regular references. Yay! Right. RefCell keeps track of how many ref and refmute smart pointers are currently active. Every time we call borrow, the RefCell increases its count of how many mutable borrows are active. When a ref goes out of scope, the count of immutable borrows goes down by 1. Yep, just like the compile time borrowing rules, RefCell lets us have many mutable borrows or many immutable borrows or one mutable borrow at any point in time. If we try to violate these rules rather than getting a compiler error as we would with references, it'll just panic at runtime, so yeah, don't do that. Right. I love like the little like Ferris panic, it's so good, but yeah. Yep. We're deliberately trying to create 2 mutable borrows active for the same scope. Yep. Yeah, so that'll just like be illegal because you're doing 2 borrow mutes. Don't do that. Create a variable 1 borrow for ref mute, smart pointer, yep. Yeah. Panicked, yep. Ferris be cute, yeah. Oh shit, no, I forgot. Bah! There. Oh. I've got a little buddy here. Ah. Can we have the Lemma Color Ferris? Yeah, I completely forgot about Lemma Ferris. Whoops. Ah. I'm actually gonna... I'm quickly just letting Kira know. Yeah, just like... Yeah. Just sending a bit of feedback to Kieran because it's really good and just gotta like configure it and use it in like a production environment before it's like fully ready to go. Yeah. There. Yeah. If that panic just say, well, yeah. Catching borrowing errors at runtime rather than compile time means that you would find a mistake in your code later, and possibly not until it was delayed or deployed to production. Also, your code would incur a small runtime performance penalty as a result of keeping track of borrows. However, using RefCell makes it possible to write a mock that can modify itself to keep track of the messages. Yep. You can use RefCell despite its trade-offs to get more functionality than regular Rust provide. Yay! Okay, yeah. Multiple owner... Yeah, then you can combine ref counts and ref cells. Yep, so... common way to use ref cells in combination with ref counter, yay. All the RC lets you have multiple owners of some type, but it only gives immutable access to that data. If you have an RCT that holds a ref cell, you can get a value that can have multiple owners and that you can mutate, yay. Yeah. Back over and I should put... Yeah, I'm just gonna grab this all back. Just because I took out that code and this is a lot of like wrapper code, whoops. Yeah, yeah, fine, I can write it, but yeah. Drive bug on list cons RC L 2 RC list nil. Then use create list cons nil standard cell ref cell. I can't say because I have work in proc 7 hours, so I should be asleep, but wanted to come say hi. Hello, Jasper! Yeah, it's great to have you here. Third RC. Yeah, then. Yeah, sleep is for the weak. No, Jasper, get some sleep. Take the fuck care of yourself, okay? Yeah, let value RC to ref L 5. Let A equals RC on RC and value RC nil. That good, right? Oh, not console. There. Illegal? Yes. Let be. Yeah. Good night, love you all. See ya, Jasper. Yeah. Cons RC 2 ref cell 3 RC own A B equals cons RC new ref cell new 4 RC clone A value borrow mute plus equals 10. Right, and print ln a after equals a after bracket and question, and then debug a ln b after equals question mark bracket b println after bracket colon question mark bracket quote b. There. Run. Right, so yeah. Yay! And just because I want to make sure, yeah, that should be 15, 315, 415. Yep. Yay! Ah! We create a value that's an instance of RC refcell I32 and store it in a variable named value so we can access it directly later. Ah. Yep. Then we create a list in A with a cons variant that holds value. We need to clone value so both A and value have ownership of the inner 5 value rather than transferring from value to A or having a borrow from value. Wrap the list A in an RCT so when we create list B and C, they can both refer to A, what we did in list 18. Yeah. Yep. After we've created the list in A, B, and C, we add 10 to the value in value by calling borrow mute. Uses auto deref to deref RCT to inner ref cell. Borrow mute returns a ref mute t smart pointer, and we use deref operator on it and change the inner value. When we print A, B, and C, we can see that they all have the modified value of 15 rather than 5. Yeah, gonna leave the stream up because it's not gonna like limit voices nice and comfy. Oh, what, hun? Yeah. Okay. Yep. This technique is pretty neat. Yep. By using refcelT, we have an outwardly immutable list, but we can use the referred methods on refcelT that provide access to its interior mutability so we can modify our data when we need to. Runtime checks of borrowing rules protect us from data races, and it's sometimes worth trading a bit of speed for this flexibility in our data structures. Named has other types that provide interior mute, such as cell, which is similar except instead of giving refs values copied in and out. Also mutex, which offers interior mutability that's safe to use across threads. Yay, mutable exclusions. We'll discuss in chapter 16. Check out docs for more details. Reference cycles can leak memory, oh no! Here's the issue with, like, pointers and such. Rust memory safety guarantees make it difficult, but not impossible, to accidentally create memory that is never cleaned up, known as a memory leak. Preventing memory leaks entirely is not one of Rust's guarantees in the same way that disallowing data races at compile time is, meaning memory leaks are memory safe in Rust. Right. We can see that Rust allows memory leaks by using RC and refcell. It's possible to create references where items refer to each other in a cycle. This creates memory leaks because the reference count of each item in the cycle will never reach 0 and the values will never be dropped. Oh no! CPython is a GC that sweeps through them every once in a while, yeah. Right, so yeah, right, let's look at how a reference cycle might happen and how to prevent it. So, yep, start with listing them in a tail method in 55. Okay, so yeah, we've got list, you know, we've got an impl list, so impl list untail and up and self option. We should, what we're doing here is clear this out. So right now we're doing an I32 and a refcell RC list, okay. Option and refcell RC list. Oh boy. Match self fonts blank item item none. All right. Okay. What? Right, anything else we got to do here? So, using another variation of list def, yep. So, second element is now refcell RC list, meaning that instead of having the ability to modify the I32, we want to modify which list value a cons variant is pointing to. Also adding a tail method to make it convenient for us to access the second item if we have a cons variant. Right, so let's cause some problems. Let A equal RC new cons 5 refcell new RC new nil 4 parentheses println A initial RC count equals RC long count A ln A next item up a tail, then let B equals RC new fonts and refcell new RC A println A RC count after B creation the RC strong count and A ln the initial RC count equals RC strong count B until n I hit open paren twice instead of close paren, then println in item up up tail if let some link a tail start link borrow mute RC clone B println BRC count after changing A RC strong count B not underscore boom then println ARC count after change A RC strong count A uncomment the that we have cycle it will stack a next item up tail there. Yeah. Yep, so keeping that uncommented. I forgot to standard RC standard cell ref cell rate list on nil. There, all better. Oh, bang. Bang. Oh, why is there an extra space there? How many? Why are you? Oh no. Ah. Bang. There. Yeah, So now, if I run this. Yep, so initial RC count, then nil, then 2, 1, 5 nil, 2. Yep, ref count of the RC list and instances in both A and B are 2 after we change the list in A to point to B. The end domain Rust drops the variable B, which decreases the reference count of the RC list instance from 2 to 1. Memory that RC list has on the heap won't be dropped at this point because its count is 1, not 0. Then Rust drops A, which decreases the reference count of RC list from 2 to 1 as well. This instance's memory can't be dropped either, because the other RC list instance still refers to it. The memory allocated to the list will remain uncollected forever. Oh no, that's not good. RC loops, yeah. You uncomment, yep. Yeah, so if you do this, you're gonna get a stack overflow. Yep. Got a stack overflow, yep. Yeah, that is very, very, very long. Stack overflows are not great. Yep. Right after we create the ref cycle program ends, consequences aren't very dire. However, if a more complex program allocated a lot of memory and held onto it for a long time, it used more memory than needed and might overwhelm the system, causing an out-of-memory error. Creating reference cycles is not easily done, but it's not impossible either. If you have ref cell values that contain RCT or similar nested combinations of types with interior mute and reference counting, you must ensure that you don't create cycles. You can't rely on Rust to catch them. Creating a reference cycle would be a logic bug in your program that you should use automated test code reviews and other software development practices to minimize. Yep. Also reorganize your data so that some references express ownership and some don't. You can have cycles made up of some ownership relationships and some non-ownership ones. Only the ownership ones can affect drops. Yep. We always want cons variants to own their list, so reorganizing isn't possible. So let's look at an example using graphs made up of parent nodes and child nodes to see when non-ownership relationships are appropriate to prevent reference cycles. Okay. Alright, turning an RC into a weak. Okay. Demonstrate calling RC clone increases strong count. Yep. And only cleaned up strong is 0. Strong count 0. You can also create a weak reference to the value within an RC by calling downgrade and passing a reference. When you call downgrade, you get a smart pointer of type weak T. Instead of increasing the strong count in the RC by 1, calling downgrade increases the weak count by 1. Okay. Uses weak count to keep track of how many weak references exist. Similar to strong count. Difference is weak doesn't need to be 0 to be cleaned up. Okay. Strong is how you can share ownership of an RCT. Weak don't express an ownership relationship. They won't cause a reference cycle because any cycle involving weak references will be broken once the strong reference count of values involved is 0. Because the value that weak references might have been dropped, to do anything with the value that a weak is pointing to, must make sure the value still exists. Do this by calling the upgrade method on a weak instance, return an option RCT. Okay. You'll get a result of some if RC has not been dropped and none if it has. Because upgrade returns an option, Rush will ensure that some and none cases are handled. Yay! No invalid pointers. Other than using a list whose items know only about the next item, we'll create a tree whose items know about their children and their parents. Okay. So, let's clean stuff up. Alright, so with the debug, we're going to construct node. Also put use standard cell ref cell, that type of cell, yep. Standard RC. All of you can go away. You have value I32 children ref cell spec parse node. That is these are certainly some types. These are certainly some types. Oh boy. Okay. We want a node to own its children, and we want to share that ownership with variables so we can access each node in the tree directly. To do this, we define the vectee items to be values of type RC node. Also want to modify which nodes are children of another node, so we have a ref cell and children around the vec RC node. Yay! We're getting into Rust types, yeah. Alright. Next we'll use our struct_def and create one node instance named leaf with the value 3 and no children, and another named branch with the value 5 and leaf is one of its children. Alright, so let leaf RC new node value 3 children ref cell back. Boom. Let branch RC new node value 5 children, F cell, back, arse, and leaf. Da. There. No, wrong. Ah. Clone RC node and leaf and store then branch, meaning the node and leaf now has two owners, leaf and branch. Okay. Ah. Okay. You can get from branch to leaf through branch children, no way to get from leaf to branch. Leaf has no reference to branch and doesn't know they're related. Want leaf to know that branch is its parent, we'll do that next, okay. Make the child node aware of its parent, we need to add a parent field to our node def. Really like my computer to stop crashing. At least it's like my psychic laptop and not like my stream computer that's randomly crashing things. That would be awful. Yeah. Trouble's deciding the type of parent. Can't contain an RCT because that'd create a reference cycle. Pointing to branch and branch children, pointing to leaf, which would cause them to 0. But we've got both RC and weak. So means parent a ref cell weak node. There. Alright, so, yep. So now we need to put new things in our structure. So, now, parent, ref, cell, new, weak, new, there. Then, you're good now. Let's println, if parent, leaf, parent, borrow, upgrade, there. Then we can here, so parent, ref, cell, new. Down here we can do star leaf, parent, borrow, RC, downgrade, branch, println, parent, if parent, borrow, upgrade, there. Now, run that. Bang. Go. Yep. So yeah, previously it was none, then we've got some, yep. Only weak, yep. Yay! Hooray! Alright, so yep, that is a lot of stuff. Yeah. But oh well. Lack of infinite outputs code. Yeah, I know. When we print a parental leaf again, we'll get some variant holding branch. Now leaf can access its parent. Yay! Yeah, it's not an infinite reference cycle, so yay. Then, alright, visualizing changes to strong and weak count. Let's look at how the strong and weak count values of the RC node instances change by creating a new inner scope and moving the creation of branch into that scope. By doing so, we can see what happens when branch is created and then dropped when it goes out of scope. So, yeah. Got that, yep. So what we'll do here is up. Split it out this time. Right, so wrong, dumb, RC, wrong, count, leaf, weak, count, count. There. Boop. And we're gonna this side a block. Boom. Can I just have all those? Yeah, I can. Good. Right, so got this. Parent bar mute, yep. Downgrade. I've got println is actually just the same as this. Copy it. Yeah, we've got that one, and then this one is branch. 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 And down here at the end, boom. Boom. Let's go. Right, so looks all good. So start with so leaf strong 1 weak O here. Then branch strong 1 weak 1. Leaf strong 2 weak O. And leaf parent is none because we get rid of the branch, and leaf strong 1 weak O. Yay! Looking good. After leaf is created, its RC node is strong count of 1, weak count of O. Inner, we create branch and associate it with leaf, at which point when we print out the counts, RC node and branch will have a strong of 1, weak of 1, yep. When the inner scope ends, branch goes out of scope and the strong count decreases to O, so node is dropped. Yay! No more memory leaks. Try to access the parent of leaf after the end of the scope, we'll get none again. At the end, RC has a strong count of 1 and a weak count of O, because variable leaf is now the only reference to the RC node. Yay! All of the logic that manages the counts and value dropping is built into RC and weak, but in their implementations of drop. By specifying the relationship from a child to its parent, should be weak, you're able to have parent nodes point to child nodes and vice versa without creating a reference cycle and memory leaks. Yay! This chapter covered how to use smart pointers to make different guarantees and trade-offs from those Rust makes by default with regular references. Box has a known size and points to data allocated on the heap. RC keeps track of the number of references to data on the heap so that data can have multiple owners. RefCell, with its interior mutability, gives us a type that we can use when we need an immutable type but need to change an inner value of that type. Also enforces the borrowing rules at runtime instead of compile time. Also discussed were deref and drop, which enable a lot of the functionality of smart pointers. We explored reference cycles that can cause memory leaks and how to prevent them using weak. If this chapter has piqued your interest and you want to implement your own smart pointers, check out the Rustonomicon for more useful information. Alright, looks like Rustonomicon's currently out of date, but this is where the chaos happens. Alright, yeah, the Rustonomicon is cool. It is basically how to do unsafe Rust, because you're gonna need that sometimes. Yeah, you are just gonna sometimes need some unsafe code. So I would very much like to check out stuff in here at some point. I would have a lot of fun just looking through this. I'm not sure I'd do it on stream, but yeah. Anyway, next we'll talk about concurrency in Rust. You'll even learn about a few new smart pointers. For about half an hour, I can at least get like a bit into the concurrency stuff. Yeah. Handling concurrent programming safely and efficiently is another of Rust's major goals. Concurrent programming, where different parts of the program execute independently, and parallel programming, where different parts of a program execute at the same time, are becoming increasingly important as more computers take advantage of their multiple processors. Historically, programming in these contexts has been difficult and error-prone. Rust hopes to change that. Woo! Initially, Rust thought that ensuring memory safety and preventing concurrency problems were two separate challenges to be solved with different methods. Over time, the team discovered that the ownership and type systems are a powerful set of tools to help manage memory safety and concurrency problems. By leveraging ownership and type checking, many concurrency errors are compile time in Rust rather than runtime. That's cool. Rather than making you spend lots of time trying to reproduce the exact circumstances under which a runtime bug occurs, incorrect code will refuse to compile and present an error explaining the problem. I like that. You can fix your code while you're working on it rather than after it's been shipped to prod. Woo! This concurrency allows you to write code that's free of subtle bugs and is easy to refactor without introducing new ones. It will refer to many problems as concurrent rather than being more precise by saying concurrent and or parallel. If this book were about concurrency and or parallelism, we'd be more specific, but yep, concurrent is just like a good blanket term for the purposes of the book. Many languages are dogmatic about the solutions they offer for handling concurrent problems. Erlang has elegant functionality for message passing, but only has obscure ways to share state. Supporting only a subset of possible solutions is a strategy for high-level langs, because high-level lang promises benefits from giving up some control to gain abstractions. However, lower-level langs are expected to provide the solution with the best performance in any given situation, and have fewer abstractions over the hardware. Therefore, Rust offers a variety of tools for modeling problems in whatever way is appropriate for your situation and requirements. Alright, so how to create threads, message passing concurrency, shared state concurrency, and the sync and send trait. Okay. Alright, this chapter. Oh wow, yeah, smart pointers was really, really long, Jesus. I might not get the entire way through, but I want to get at least a bit of it. Might run over a little. Yeah. In most current operating systems, an executed program's code is run in a process, and the operating system manages multiple processes at once. Within your program, you can also have independent parts that run simultaneously. These are called threads. Splitting the computation in your program into multiple threads can improve performance because the program does multiple tasks at the same time, but it also adds complexity, not surprisingly. Doing a lot of things at once is complex. Because threads can run simultaneously, there's no inherent guarantee about the order in which parts of your code on different threads will run. Okay. This can lead to problems such as race conditions, deadlocks, and unreliable bugs. Networking is haunted, and that's because networking is inherently concurrent. Yeah. Alright. Rust attempts to mitigate the negative effects of using threads, but programming in a multi-threaded context still takes careful thought and requires a code structure different from programs running in a single thread. Basically, gotta be careful, unsurprisingly. Yeah. I'm messing around with like one of my stim toys here. It's really nice just having tons and tons of stim toys around me all the time. It helps a lot. Alright, programming languages implement threads in a few different ways. Many operating systems provide an API for creating new threads. The model where a language calls the APIs to create threads is sometimes called one-to-one, meaning one operating system thread per one language thread. Many programming languages provide their own special impl of threads. Programming language provided threads are often known as green threads, and languages that use these will execute them in the context of a different number of OS threads. Yep. This is called M-to-N model. There are M green threads per N OS threads, and M and N are not necessarily the same. What the fuck are hyperthreads? What? Yeah, like... hyperthreading, it's Intel stuff, okay. Got it. Yep, alright. OS, yeah. Okay, for each physical core to logic cores shares workload, yeah. Hyperthreading is having more logical threads than physical threads, yeah. Got it. Hooray, proprietary Intel stuff. Yep, each model has its advantages and trade-offs. The trade-off most important to us is runtime support. Runtime's confusing and that can have different Yep. One Intel restricted i9's Wii. Yeah. In this context, by runtime we mean code that is included by the language in every binary, okay? This code can be large or small depending on the language, but every non-assembly language will have some amount of runtime code. For that reason, colloquially when people say a language has no runtime, they just mean a small runtime, like C has a runtime. Yeah, like, smaller runtimes have fewer features but have the advantage of resulting in smaller binaries, which makes it easier to combine the language with other languages in more context. Although many languages are okay with increasing runtime size in exchange for more features, Rust needs to have nearly no runtime and cannot compromise on being able to call into C to maintain performance. Fun. Yep. The green threading end-to-end model requires a larger language runtime to manage threads. As such, the Rust standard lib only provides an implementation of one-to-one threading. Because Rust is a low-level language, there creates implement end-to-end if you would rather trade overhead for aspects such as more control and lower cost of context switching. Alright. So, we've got stuff. Oh boy, it's time. Yeah, we're gonna be using time stuff. Use standard thread. Standard time duration. Thread spawn. Ooh, closures, okay. Alright, so use... Yeah, I think it is pretty cool, that, like, you just use a closure for threads. Neat. For I in 110, println, I number sum from the on thread, I, then thread the duration from 1. Right? Yeah, that is what we're just having there. Up. Then for I in 1.5, println I number from the main thread. I thread duration from these 1. So now I can run this and it should, like, kind of mix them up. Yeah. So 1 main, 1 and 2 spawned, 2 main, 3 main, 3 spawned, 4 spawned, yeah, 5 spawned, done. Yep. Oh, hey, 1, 1, 2. Yep, so 1 main, 1 oh, we've actually got ours a bit scrambled up, but running about the same speed. But yeah, that's neat. Because that's the thing with concurrency. It's unreliable! Yeah, Pause the thread sleep. Force a thread to stop its execution for a short duration, allowing a different thread to run. Okay. Threads will probably take turns, but that isn't guaranteed. I'm very late, but hyperthreading is I9 only now? Yeah. Right. Threads will probably take turns, not guaranteed. Depends on how your OS schedules. In this run, the main thread printed first, even though the print from spawn thread appears first in the code. We told it to print till IS9, but only got to 5 before main shut down. Yeah, that's a thing. As soon as your main thread ends, your code's done. Yep. If you run this code and only see output from main thread or don't see any overlap, try increasing the numbers and the ranges to create more opportunities for the OS to switch threads. Okay. Got it. Yep. Alright, so code listing 16.1 not only stops spawn thread prematurely most of the time, but also cannot guarantee spawn thread will get to run at all. There is no guarantee on thread run order, ever. Which is interesting. Right. It can fix the spawn thread problem not getting run completely by saving the return value of thread spawn in a variable, so let handle. That is a join handle. Owned value that when we call join method on it will wait for its thread to finish. Okay. Yeah, and that returns a result, it looks, yeah. Well, with tricks you can force a thread run order, yeah. But like naturally there's no guarantee. So handle join wrap. Yeah. Yay. So yep, now this will boom. So one main, one spawn, two spawn, two main, three spawned, four spawned, four main, five spawned, 6, 7, 8, 9. Yay! Woohoo! Alright, yeah. Two threads continue alternating, but the main thread waits because of the call to handle join and does not end until the spawn thread is finished. Alright, yay. So let's see what happens when we instead move handle join before the for loop, okay. Now, I have a feeling I know what's gonna go on here. Yep, 1 through 9 from the spawned, then 1 through 4 for the main, yay. Yep, that's threads running in order. Yep, can affect whether or not your threads run at the same time, yep. Using move closures with threads, ooh. Move is often used alongside thread spawn because it allows you to use data from one thread in another. That's cool. Mention we can use move before the param list of closure to force closure to take ownership of the values it uses. Technique is especially useful when creating new threads in order to transfer ownership of values from one thread to another. Yep. Closure passes thread spawn takes no args. We're not using any data from the main thread. To use data from the main thread, spawn thread's closure must capture the values it needs. So, let's see. Back. 1, 2, 3. Not 30. There. And we'll just, and here's vector, close, go D, semicolon, and I'll join unwrap. And you are illegal! It tells you, because that is part of threading. Yep. Function requires argument type to outlive static. Yeah, it is borrow checker. Yeah. So may outlive borrowed value v there. Yep. Because it's another thread. Yeah. Hooray, borrow checking. I think it's really cool that like borrow checking works for both memory and like concurrency. That is a neat thing. I like that. Yeah. Okay. Rustin first how to capture VM because println only needs a ref it tries to borrow, but we really need you to move, so... Yep, and like if we tried to drop V out here, that'd be an issue. Yeah, that'd be an extra issue because that hasn't executed yet. Whoopsies. Possibility spawn thread would be immediately put in the background without running at all because, yep. Spawn thread is reference to V inside, but the main thread immediately drops V using drop. Then when the spawn thread starts to execute, V is no longer valid. Ah. Yeah, just, move it. Run. Yep, now that works just fine. Yay. Right. Don't need the duration right now. But yeah. What would happen to the code in listing 16.4 where the main thread called drop if we use a move? Move fix that case? Nope, we'd get a different error because then you're trying to drop something that you don't have ownership of anymore. Yay, get an error from code because Rust was being conservative not borrowing, but now we move, so yeah. With a basic understanding of threads and the thread API, let's look what we can do! One increasingly popular approach to ensuring safe concurrency is message passing, where threads or actors communicate by sending each other messages containing data. Here's the idea in a slogan from Go. Do not communicate by sharing memory, share memory by communicating. Right? One major... Yeah, this reminds me of... something. Found a 10C16T. Fun. Yeah. Yeah, that reminds me of something in, like, Python. I will have to find quick. Yeah. Yeah. Yep. Yeah, yeah, like, in Python, yeah, Python has, like, for example, like, the simple queue, which is, from what I can mostly tell, basically, you're just putting things into a queue and effectively they're messages. There's not, like, really a yeah. Because they're just objects and Python's a VM, I think it might copy them between threads, but I'm not entirely sure. Yeah, just, like, using that was, like, a big thing in getting all my stuff to actually work properly with, like, the progress tracking and all that in GBS Toolkit, which I'm still really proud of, TBH. I can't wait to, like, do more, like, full projects on stream again. Like, I have had to take a bit of a break just because I was really getting burnt out on my current projects, and I haven't really had the time or focus to get back to any of them yet. Like, I really do want to work more on Soul and Silicon soon. I think, like, I really do want to do that, but it's just hard. Like, I have to do a lot of writing and it's difficult. Yeah. JC, I mean, that's the only exception recently? Yeah, only has hyperthread for one cluster of CPUs. Interesting. Yep, so the channel, a programming concept Rust standard library provides an impl of, yep. Yep, imagine a channel in programming as being like a channel of water, such as a stream or river. Oh boy, don't talk to me about streams. I'm a Java dev previously. Put something like a rubber duck into a boat or a stream, will travel to the end of the waterway. Yep. So there's two halves, a transmitter and a receiver. Transmitter is upstream, yep. Receiver is downstream. One part of your code calls methods on the transmitter, and another part checks the receiving end for arriving messages. Yep. I also think the number after the I is meaningless these days, yeah. Yeah, so this does, like, sound at least pretty much like the queue from Python I was... Yeah. Ah, ears clogged. Ah. Ah. I don't know why. Yeah. Here we'll work up to a program that is one thread to generate values and send them down to a channel, and another thread that will receive the values and print them out. We'll be sending simple values between threads using a channel to illustrate. Once you're familiar with the technique, you could use channels to implement a chat system or a system where many threads perform parts of a calculation and send the parts to one that aggregates. Yeah, that is basically what I was doing in, like, GBS Toolkits tonight. So, this won't compile. Okay, so, standard. Once you're familiar, you could use channels to implement chat or system where many threads perform parts. Yep. Think MPSC, then let EX RX. You're angry because we need types. Multiple produce a single okay. Yep. Channel can have multiple sending, but only one receiving. Got it. Daydreams about two ferrets floating ducks to each other. That's cute as hell, TBH. Yep. Only one receiving end. Yeah. Start with a single producer from now, but we'll add multiple producers when we get this working. Function returns a tuple, first element of which is sending and second is receiving. TX and RX, yep. Yep. Traditional, yep. Don't know why, but oh well. Out of scope for the book. Name our variable such int, yep, using a let with pattern that destructures the tuples, yay. I think, yeah, I like tuple destructuring. It's really cool. Yeah, that just gives tuple sender receive. How do you, like, change, like, keybinds and... How do you adjust keybinds? Yeah, oh, well, I'll figure it out later, but yeah. Yeah, well, channels are one way, so only one ferret would be receiving the ducks, yeah. But yeah. So, then we can... Yeah, so right now it just needs some type inference. Luckily, Rust is really good at type inference. Thread on let val equals thing not tx send val unwrap. I wish you like. Yeah, keybinds, Control K, Control S, or file premises keybinds. Thank you. Oh yeah, I forgot to add use thread. Boom. Why are you angry? Now you're okay. Alright, yeah, because no semicolon means that that's the return value. Whoops. That is like something I do think I'm just gonna keep getting caught on with Rust, is like final statement in block is return value. But oh well. They've got explicit returns, I'm fine with that. Thread spawn to create new thread, and then using move tx into the closure so the spawn thread owns tx. Needs to own the transmitting end of the channel to be able to send messages through the channel. Transmitting end is send that takes the value we want to send. Send returns a result TE, so if receiving end's already been dropped, no, send a value, the send op will return an error. We're just calling unwrap to panic, don't supercard. I'm used to not needing to use return to honestly, it's really nice, yeah. Yeah, it's just like, I'm just like very ADHD and can like forget or not manage to type semicolons or such, but yeah. Like, I'll probably get used to it over time, it's just like a bit of a learning curve, you know? Yeah. Then, let receive rx xd unwrap ln dot boom. Ah. Oh, heck. Rx not rc. Got high. Yay. Woohoo. Feel sober votes have to type return in a timely land in C++. Yeah. Yeah, like, I think for me it's a lot more situational where, like, if it's like a function, I will, like, if it's a function, I'll usually use like a hard return. If it's just a lambda or like a branch and pattern matching, I'll use a soft return. It just like, yeah, my mind just works a bit better with like a hard return from a function. Oh, I still forget to put semicolons half the time. Most times it's because I keep switching windows to read docs or something. Yeah. Yeah, like, I'm not saying that like I'm never gonna use like soft return. I just think that like hard returns are useful in some cases. So there's recv and try recv. Recv will block the main thread and wait until a value is sent, okay. Then try will not block, okay. Really? Alright. Makes sense. Yeah. Yeah, no, this is basically exactly what I had, this is basically exactly what I had in, like, GBS Toolkit, so, like, with, like, the Q, which is, like, equivalent, which is basically equivalent to the, TXRX, like, I just basically had a loop of, yeah, checking if there was anything else in the queue, and stuff like that, yeah. Yeah. Like, getting pull or whatever, yeah. Alright. Yeah, got high, yay. Channels and ownership transference, okay. Ownership roles play a pivotal role in message sending because they help you write safe concurrent code, yay. Preventing errors in concurrent programming is the advantage of thinking about ownership. Let's do an experiment to show how channels and ownership work together to prevent problems. We'll try to use a val value in the spawn thread after we've sent it down the channel. Print ln val is val. So this is illegal because val is like, yeah, val is trying to borrow, but it was already moved from here. Makes sense. We try to print val after we've sent it down the channel by txsend. Applying this would be a bad idea. Once the value has been sent to another thread, that thread could modify or drop it before we try to use the value again. Alright, so like, yeah. Alright. Potentially, other threads mods could cause errors or unexpected results due to non-existent data. However, Rust gives us an error if we try to compile the code listing in 9. Yep, that we saw that. Yeah. Concurrency mistake has caused a compile time error. Yay! Then takes ownership of its parameter, and when the value is moved, the receiver takes ownership of it. This stops us from accidentally using the value again after sending it. Ownership checks everything is okay. Yay! Right. Sending multiple values and seeing the receiver waiting. Okay. Now what we're gonna do is we're gonna let vals equal back string from I string from string from the thread. Oh, here we go. Channels look like Java blocking queues. I should. I definitely should adjust things so that, like, yeah. I'm actually gonna do that right now. But let me. Let's open paste link. I open left and right. Left. Yeah, those are good. I open right. Yep. All right. Yep. I X. I Y. Brow height. Yep. Okay. Got it. Mouth smile. Mouth open. What if I? So. Wait, no. Alright, so there's a Alright, so I'm gonna. Testing 1, 2, testing 1. Testing. About 0.8, yeah. Testing 1, 2, testing 1, 2, testing 1, 2. Ooh! That looks a lot better, but yeah. I do think I want, like, because, like, the mouth open like, correlates with, like, shrinking pupils if I open it a lot. I think I do want that, like, changed just a bit, but yeah. Okay, yeah. That is a lot. How about 0.8? She sells seashores by the seashore. The quick brown fox. Oh, that's a good one. The quick brown fox jumped over the lazy dog. Alright, yeah. That's a lot better. Yeah, I am, yeah, a lot happier with that one. Might make you go to. How about, so now, yeah. Alright. It won't cap out as quickly, but, it will start a bit quicker. That's a lot better. Yeah, I'm really yeah, that's much, much, much better. I've got the smile frown, yeah. There. Looks a lot better, yay! Okay. 9 o'clock, okay, yeah. I'll keep going until, like, this section is done, but yeah, I'm gonna just, like, keep tweaking stuff, like, I think I do definitely want, like, eyebrows to be, yeah, exclusive. I want them to be exclusive to, like, the, look, sounds good. Yeah, I want them to be, like, exclusive to eyebrow raising and not just to, like, and not to, like, open mouth, but yeah. Oh, I should, does look like they hit phase, but yeah. Yeah, it might be thing with also having brow raise with open mouth setting. Yeah, I'm really glad that I'm, like, able to, like, just give this a few little tweaks while I'm live and not having to pull it into Unity or anything. Yeah. We're, like, decently done. Yeah, I might, like, do the next page as well, I'll see, but yeah. Yeah, we've got, now, instead of just that, gonna, for vowels, x, and val, unwrap, red, duration. Yay, auto imports from x on. Yay, and for rx println dot received. Right. Ooh! Generators! Fuck yeah! Generators are cool and good. I like generators. They're nice. Yeah, I like that. Yeah, spawn thread is a vector of strings that we want to send to the main thread. We iterate over them, sending each individually, and pause between each by calling thread sleep with a duration of 1 second. In the main thread, we're not calling recv function explicitly anymore. Instead, we're treating rx as an iterator, or more specifically, a generator. When running in 1610, you should see following input with a 1 second pause. Yep. Because we don't have any code that pauses for or delays in the for loop, the main thread, we can tell that the main thread is waiting to receive values from the spawn thread. So, yep. And now multiple producers. So let x1 equal x clone. So now you're gonna 1 and Rust generators are still unstable. Their channels can act like them when multi-threading. Yeah. Yeah, I like generators. They're cool. But yeah, then thread spawn move let vals equal back string messages for you. Semicolon for val in vals x val wrap. Boom. Yeah, one of those things that probably won't be added for a while. Yeah, oh well. Rust generator. Yep. Yeah, Array coroutines, yep. Yeah, ergonomic definition for iterators, other prims, yeah. Yeah, currently unstable, require further RFC for stabilizations, yeah. I like generators, they're cool. Oh, that's my other alarm, okay, yeah. Yeah, no, generators as a concept are neat. Yeah. RFC 23, yep. Routine and generators are cool. Yep. Just making sure everyone's on board, but yeah. If when Rust adds generators, I can think of a few situations I'd already use them, yeah. Alright. This time before we create the first spawn thread, we call clone on the sending end of the channel. This will give us new sending handle we can pass to the first spawn thread. Pass the original sending end of the channel to a second spawn thread. This gives us 2 threads, each sending different messages to the receiving end. Let's run that. I, not, put the sleep in. Thread, sleep, duration. 1. Boom. And more from messages or the new thread. Yay. Yay. Alright, yay. Might see the values in another order, depends on the system. This is what makes concurrency interesting as well as difficult. You experiment with thread sleep, it gives various values in different threads. Each run will be more non-deterministic and create different output each time. Let me quickly check how long this one. Oh, that's a long one. My throat is hurting just a bit, but yeah. I am very happy I've gotten to like concurrency stuff because I have wanted to do concurrency for a while. Alright, so yeah, Anyway, yeah. How about we just wrap things up? That looks so good on this street. Beep, beep, beep. Yeah, yeah, I am very, yeah, very happy with, like, how I'm going on in how, like, I'm going with, like, learning Rust. I am having a lot of fun. Just a cool language. Yeah, let's see who is live. Da, ba, 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 da, ba. Da, ba, da. Folks. Yeah. Anyone got, like, Rex? Yeah, go over to Lily Blue. I'm gonna go raid Lily Blue, I think. But yeah, so we're just gonna go with our usual soft robo raid. With a hug. Yeah, no, this model is really good. I am just having so much fun with it. I can't wait until it's, like, fully done. Yeah, raid 5-3. Thank you all so much for watching, hanging out, joining in. I'm having a ton of fun here with this. I've had a ton of fun tonight. Thank you for everyone who hung out. Yeah, I'm glad that everyone's enjoying my model. I will have a few more tweaks for it in the near future. Look forward to those. But yeah, when we get over to Lily Blues, please do not hesitate to drop them a follow, because they're pretty cool, pretty neat. Yeah, with that, I am gonna send y'all on over. Join me back here tomorrow, where I'm gonna be doing some more speedrun attempts for Donut County. And with that, I'm gonna finish things off. How about we get this raid started in 5, 4, 3, 2, 1.